Okay, hi everyone. Today we're going to look at 4.5 points of inflection and in particular curve sketching. And we're going to use some of the skills from yesterday's lesson to answer 3 questions, 2 without a calculator and then 1 with our CAS. First up, as a warm-up, I'd like you to consider the problem on the board. A bit of an unusual Venn diagram here, and you'll see lots of different functions. And what I'd like you to do is see if you recognize those and come up with basic equations for each of them. So work around each of those graphs and see if you can identify an equation that would fit the shape and then also fit its location on the Venn diagram. Pause the video to have a go, and then we'll look at the more interesting points together after that. So pause the video. Okay, we're going to look at the solutions now, or some solutions to these graphs, and in each case the most simple version. I want to draw your attention to a couple of things in particular. So the first thing is that we can see some examples of graphs which have the second derivative being equal to 0, but that are not points of inflection like we saw yesterday. So here we have our buckets, if you like, the examples where the function and the gradient of the function are both 0 at the point we're interested in, but also the second derivative is 0, meaning it's barely changing at all, and we get this really flat shape. Then we have some more curious examples where we have discontinuities, where we have mod x and minus mod of x. The problem we have there is that d2y by dx squared is just not defined at this point because the gradient is not defined. The graph is discontinuous. And then, of course, we have straight lines where the second derivative doesn't exist, that the function is not changing, the gradient is not, or the gradient is not changing. If we look at a couple of the other examples here, if we look at fractional powers, we can see that they have this concave down shape approaching the point x equals 0, but there is also this discontinuity there, and the fact that we cannot define the gradient well at this point x equals 0. So the gradient's defined elsewhere, but not at the point where x equals 0, and we can see the similar version up here for the negative version of that. You can see actually that this point about functions not being differentiable at particular points is relevant in a couple of other cases. So over on the left hand side here we have a change in concavity for a reciprocal function 1 over x, but that happens either side of an asymptote rather than a point of inflection, and that makes sense to us, that that's an exception to our rule, that the function itself is not defined at that point, but we can still get a change in gradient and a change in second derivative in concavity. So hopefully a really nice summary for you there of both why this general rule about identifying the nature of stationary points works in most cases, but also some examples of the various exceptions to that. What we're going to do now is we're going to go onto our notes, and we're going to look at 4.5 and 3 relatively long questions. I'd like you to have a go at each of them before I get onto them. The first 2 non-calculator. So here we have a function that has 3 parts, a reciprocal, a constant term, and then a log term. And we are going to use all our tools to try and sketch it. Pause the video and have a go yourself in your workbook, and then we'll go through a version together. Okay, so as I approach this, the first thing I notice is that we have a restricted domain, and because this is positive real numbers, we notice 0 isn't included. And that's helpful for us because we can see that x equals 0 just on inspection is not defined here in a couple of different ways. And if we think about what's going to happen as we get close to 0, so for very small values of x, so as x tends to 0, I'm interested in this because 6 over x for very small positive values is going to tend towards positive infinity, because 6 divided by a very small positive number is very, very large. But actually this second term, log e of x, what we know about the graph of that is going to tend towards negative infinity. And so the question is, when we add these together, what's going to happen? And that's the most interesting thing about this question as I look at it. I don't know without a bit more analysis what's going to happen, which one of these two terms is going to be dominant for small values of x. So we have to just go to our basic tools. So we define f of x as 6 over x minus 6 plus 3 log e of x. And I'm just going to differentiate it twice because I know I'm going to need both of these. So minus 6 over x squared plus 3 over x, or in other words, factorized 3 over x squared times x minus 2. And that useful form there is going to help us identify the stationary points. But then, before I even start to worry about that too much, I'm going to find the second derivative, multiplying by the power here, which is minus 2, which is going to give me 12, reduce the power by 1, x cubed, multiplied by the power, which is minus 1, reduce the power by 1, x squared, or factorized 3 over x cubed times 4 minus x. Okay, so my basic differentiation done, I could then start to look at stationary points. So if I look at stationary points when f dash of x equals 0, that implies that x equals 2, looking at the expression here for f dash of x. And then we can find the y coordinate by substituting in x equals 2, which is going to give me 6 over 2 minus 6 plus 3 log 2, or in other words, 3 log 2 minus 3. So our coordinate is going to be 2, 3 log 2 minus 3. That's going to be our stationary point. And then after we've looked at stationary points, the standard thing that we're going to do is work out what its nature is. So I'm going to look at f double dash at 2, and substituting in here, that's going to give me 3 over 8, 2 cubed is 8, times by 2, so 3/4. Key thing is that that's greater than 0, therefore this is a local minimum. So I've got one stationary point in the domain, I've got its coordinates, and I know it's a local minimum. Next thing I'm going to do is look for any points of inflection, labeling what I'm doing really closely. So looking for f double dash being equal to 0, which, looking at the equation, definitely happens when x equals 4. And at that point, similar to what I did before, I can substitute in and work out the y coordinate as 6 log 2 minus 9 over 2, I think, as you work that through. So that's going to give me a coordinate of 4 and then 6 log 2 minus 9 over 2. And at a point of inflection, what is going to be interesting to us is what the gradient is at that point. So at this point, f dash of 4 is going to be, substituting in 4 here, I get 3 over 4 squared, which is 16, times by 2, so 3/8, which is greater than 0. So I'm looking at a positive gradient with a point of inflection, giving me some key information about what's happening there. And then I guess just to identify exactly the nature of that, what I can do is look at the second derivative on either side of 4 and to see whether it's going to be moving to concave upwards or concave downwards. But I'll think of that through as I'm doing my sketch. Then, of course, we've got stationary points and points of inflection, but the other thing is the roots here. And that is when f of x is equal to 0. So this is a tricky thing for us to analyze because of this log term, and it's going to be hard for us even to know exactly how many solutions to expect. I can imagine the graphs and think about that a little bit, but as I'm looking at this, I notice that if I substitute in 1, I'm going to get 6 over 1 minus 6. So I'm just looking at the top here, 6 over 1 minus 6, which is going to give me 0, and then log of 1 is 0. So I'm going to have a root, so x equals 1 is a root, because 6 over 1 minus 6 plus 3 log e of 1 equals 0. That gives me a little bit of extra information, but because of the combination of the reciprocal term and the log term, there's not much more I can do quickly with that without a calculator. So instead what I'm going to do is try and use the information I've got to sketch my function here, drawing my x and my y, and I still have, well, let's have a look at it. We've got an intercept at 1, and then at 2 we have a minimum, and we have to think a little bit about the coordinate of our minimum. Looking at the coordinate of the minimum, we have log e of 2. Now, e is about 2.7, so we know log e of 2 is definitely less than 1. So this y coordinate is going to be negative. It's really helpful here on non-calculated. I mean, this is tough for a non-calculated question, but it's good for us to have an understanding of these constants, like e, in order to approximate some of these values. But we have a minimum here, and then we're going to have this point of inflection at 4, and looking at the y-coordinate of that, log e of 2, it's smaller than 1, but it's bigger than 0.6, if you like, so this actually works out as positive, and at this point, you know, perhaps it is fairer for us to have a calculator to be able to evaluate some of these coordinates. But we're going to have a point of inflection here, and we knew that we had a positive gradient, so I could draw the tangent on. So we're going to have, well, a function that somehow has to have an asymptote, and then a minimum point here, meaning it's got to look like this, and then a point of inflection at this point here. And joining the dots, there's nothing really that can happen apart from a strong decline from this asymptote here, hitting the minimum, coming back up, and then we would have a second root, and that was difficult for us to identify, but a second root, and then a point of inflection up here. Okay. So labeling the points, 2, 3 log e of 2 minus 3, and the point of inflection 4, 6 log of 2 minus 9 over 2. Something like this. Okay. So, second question for us to look at, similar in style, but asking us to do something slightly different. We're going to consider a polynomial function f of x, which is a cubic, partially factorized here. What we're going to do is look at the stationary points at points of inflection, and then on one axis we're going to sketch y equals f of x, y equals f prime, and y equals f double prime or double dash. And we're going to plot that on a particular domain. So pause the video and have a go at it yourself, then I will talk you through my solution. Off you go. Okay, so a very good way to start is just to get these derivatives down. So we have f of x as 10x squared minus x cubed, f dash of x being then 20x minus 3x squared, and f double dash of x being 20 minus 6x. And of course all of these can be factorized. So I have x squared, 10 minus x for f of x. I have x 20 minus 3x for f dash. And I have 2 and 10 minus 3x. Really, those are going to be our tools for the rest of the question. Looking at part A, we're looking at stationary points. So stationary points implies that f dash of x equals 0. So that implies either x equals 0 or x equals 20 over 3. Substituting both of those in, at x equals 0, y would be 0, and f double dash of 0 is 20, which is greater than 0. So overall that tells us that the point 0, 0 is a local minimum. We repeat that trick with the second point, slightly more complicated on the substitution here. If x equals 20 over 3 and we substitute in, and this is a non-calculated question at this point, so substituting in 20 over 3 into f of x, I'm going to have 400 over 9 times 10 minus 20 over 3, which is the same as 4,000 over 9, take away 8,000 over 27. Multiplying by 3 is going to give me 4,000 over 27 when I do the subtraction. So that's for the y coordinate, and then looking at f double dash of 20 over 3, I'm going to get 2 times 10 minus 3 times this, so minus 20, which is minus 20, so that's less than 0, which tells me that this point, 20 over 3, 4,000 over 27, is a local maximum. That's my argument for part A. For part B, coordinates of the point of inflection. So we know that at a point of inflection, f double dash of x equals 0, which means that x equals 10 over 3. So halfway to between the minimum and the maximum point, meaning that substituting in y is 10 squared, so 100 over 3 times 10 minus 10 over 3, or simplified 20 over 3, 2000, sorry, this was 100 over 9 because I squared it, 100 over 9 times 10 minus 10 over 3, 2000 over 27. Interestingly, x coordinate and y coordinate both halfway between the two stationary points. So we have the coordinates now, but we want to look at the gradient at that point. So we look at f dash of x coordinate 10 over 3. More simplifying to happen here. So what we've got, 10 over 3 times 20 minus 3 times 10 over 3, 10, which equals 100 over 3. And noticeably a very steep gradient, 33.3 recurring. So we can say here that coordinates 10 over 3, 2000 over 27 is a point of inflection with gradient 100 over 3. So checking back to the question to see if we've answered it. Found the stationary points and determined their nature, yes. Find the coordinates of the point of inflection. Find the gradient at this point, yes. Then it says on one set of axes, sketch the graphs of f, f dash, and f double dash. And hopefully some of the practice that we've done on Desmos up until this point is going to help us here. So noticing that the domain is positive values only, I'm going to try and sketch my full range here, and it wants me to go up to 10. And then I'm going to look at where I've got my key points. So I've definitely got key points at 0, 0, at 10 over 3, so that's about, it's a third of this domain. So I'm going to have 10 over 3 and 20 over 3 as being my key points, meaning I tried to split it, pretty accurately into 3 sections here. And then the y coordinates I've already got for my initial curve are 10 over 3 matches with 2000 over 27. Put that in here, 2000 over 27. And if I double that, so again trying to get it roughly accurate, 4000 over 27 was the original stationary point, which was a local maximum. So if the first graph I try and draw is f of x itself, I can see it's a negative cubic. I know that that means it's going to come down from positive infinity on the negative side. Then we're coming up. We have a very steep point of inflection where it starts to change at 10 over 3, and then we come up for the local maximum, and the second root is at 10. So this function here is y equals f of x over the very specific domain that they've asked for. So that's one part of it. Then the next part would be to draw the function for f dash. So as soon as we've got a parabola, it's slightly easier. And in fact, we know that the second derivative is equal to 0, meaning this curve has a stationary point when we have the point of inflection. So first up, my zeros. My zeros are going to be where f dash of x equals 0. In other words, at the stationary points we've had before. So my graph is going to go through 0, 0, and it's going to go through 20 over 3, which is another way, knowing my symmetry, of telling me that I'm going to have some kind of turning point at 10 over 3 here. And as I'm trying to work out, I guess the only thing I need to understand is the height of that. I found f dash of 10 over 3 here, which is 100 over 3, multiplying by 9, that's 900 over 27. So it's definitely less than 2,000 over 27. So it's going to be somewhere in here. And maybe I could label it as 900 over 27. That point is going to be the maximum of my quadratic. So my quadratic is going to go up. It's going to hit the maximum there, and then it's going to come down and look something like this. You could say that that is the gradient, the graph of the derivative. You can check that a little bit. What that tells us is the gradient is always positive until we hit 20 over 3, and then the gradient becomes negative and getting steeper, which is true. And we can see here that the gradient hits 0 at the point of inflection. So that all works. Then the final thing we've got to look at is the graph of the second derivative. We can use just a simple y equals mxc form. Here we've got 20 minus 6x. So 20, where does that come in here? 2 times 27 is 54, so 20 times 57 is 540. So we're going to hit about halfway up, a little bit more than that, and it's going to have a 0 at 10 over 3 because that's where the graph of the gradient has a stationary point. So we're going to have a straight line that comes through like so, and that point there, which I should label, is 20. And this graph is y equals f double dash of x. So that's my final solution. Hopefully looks quite similar to yours. Okay. What I want to do before we just finish then for today is I just want to look at how we can use our calculator to help us solve questions. And the final thing you guys are going to do is you're going to try the exam question underneath. So I'd like you to take a moment and to take your past calculator and to have a look at the different tools we can use here to help us answer the question. Then once you've familiarized yourself with that, I'd like you to just have a go straight away with the exam question here. It's from exam 2, so you're allowed your calculator, and it's worth 7 marks. Give yourself about 10 minutes, and you can of course also use your notes. Okay, so you have hopefully tried this question now. What I'm just going to show you is one thing that I found helpful whilst doing this. So I'm going to try and get it so you can see it on the calculator as well. So as is made clear in the notes, the first thing that you should really start off by trying to do here is to define your functions. So looking at Math 3 define, I'm going to define f of x as being equal to the expression in the question here. So 6x times root x all over 3x squared plus 1. Just double check it always before inputting it, and we're done. And then what I was just going to say to you that I find useful is straight away, if I know I'm going to use it, to define g of x as being the derivative of f of x. And then I know from this point onwards that g is going to be my first derivative, and then I would actually go even further, and I would define h of x as, and I'm just going to copy this down, the derivative of g of x, which then tells me that, it gives me that h is always the second derivative. And so when I'm answering a question like this, and I know I'm always going to be substituting in to work out the y coordinates, or to evaluate the gradient at a certain point, or to solve, rather than typing in the derivatives, I can just use f, g, and h. So we've already done quite a long video for today. I'm not going to go through the solution to this in detail, but what we can do quickly is just look at the mark scheme. So I hope you've tried it yourself, and then you just give me a second. Here we go. So it was the first question on this paper in 2008 after the multiple choice, and so is relatively gentle, but the average number of marks was still 1.5, so 1.93, 4.3 out of 7, and hopefully you're confident that you can do much better than that. Using your calculator at every point to check your values should mean that you can be really accurate, and in fact the key places where people lost marks were missing out parts of the question. So failing to verify the maximum turning point using the second derivative, and just writing down 1.5 and not testing it and showing that, stating that it must be a maximum because the second derivative is negative. For not giving a polynomial equation in 1b, which is what it asked for, so you must have the polynomial part of the numerator being equal to 0, not the whole thing. And quite a few people with 1b, part 2, when using the equation solver, they were also giving the negative values that were outside the range here. So each of these, the 0.2 was also paired with a minus 0.2, the 1.7 was paired with a minus 1.7, because you've got an equation there which only has even powers, right? So for every positive solution, there's also a negative solution that goes with it, but all of those are outside the domain, and so are irrelevant. And then the final point here is that you've got to state the full coordinates, including the y values. So the final graph looks something like this, and I'm hopeful that you were pretty successful with that. So on with the exercise for today, and as always, let me know if there's particular questions that you've struggled with. Otherwise, best of luck. Okay, students, really sorry, you thought you were done. A very small amendment to my first answer here. Apologies that I realised as I was looking at this again later that this value here, the y coordinate for the first part, is negative because log e of 2, that's much less than 4.5, and so the point of inflection should actually be down here. Not a huge difference to the way I draw the graph, but in order to get full marks, I would have had to label the coordinate separately as a negative value, and actually the other root is greater than 4. So that's a little bit of a mess. I'm sorry about that, but I didn't want to go without correcting it. This coordinate is negative. Okay, best of luck with the work, and speak soon.